TEKS 9C Exponential Application Notes. So now we're going to start looking at applications of exponential functions. So before we do that, we need to learn a couple things first. So on the note section, it says remember to change percent into decimals. So anytime we see a percent in an application, we need to change it into a decimal before we can plug it into our equation. So just so you remember how to turn a percent into decimal, you have to move the decimal point to the left. So let's look at our first example. It says 6%. So right here, here is the decimal right after 6, so we have to move it 2 spaces to the left. So 1, 2. So then this would be 0.06. Okay, let's do the same thing for number 2. 2 decimal places to the left. 1, 2. This is our new decimal place. So this is 0.00010. Okay, now 0.3% into a decimal, 2 decimal places to the left, 1, 2. So this would be 0.003. Okay, so we have to keep that in mind when we are dealing with our problems. Okay, so let's look at these formulas. So we remember our standard y equals ab to the x power. This is what we've been learning all last week. And remember, we learned that a is the y-intercept, b is the growth/decay rate. So I'm going to show you what it means on these new formulas. So for growth, in order to differ from growth, you're going to see in our word problem the specific words they use. So let me go ahead and label everything. So this A is still going to be our y-intercept, but we're going to call it our initial value. So our starting point. This is our y-intercept. And then B is our rate. You'll always see rate as a percent, but we want to convert it to a decimal. So you'll see rate in our word problem as a percent, but we're going to convert it into a decimal just like we did up here on the first part of the notes. And then this x is going to label as time. Okay, so we have a as our initial value, b as our rate, x as our time, and this is going to be 1 plus since it's a growth. And then lastly, this y value is going to be our new value. So remember, a was our initial value, so our starting value. Y is our new value. So that's what we're going to solve for when we are solving these problems. We're always trying to find y. Okay. Then if you look at decay, notice the only difference, instead of 1 plus b, it's 1 minus b. And remember, this is important because our growth is when b is greater than 1, and our decay is when b is less than 1. So for growth, if we do 1 plus b, that means after we add that decimal to 1, it's going to be something greater than 1. Same with decay. After we put in that decimal for b and we do 1 minus that decimal, it's going to be a number smaller than 1. So that's in order to keep it growth and decay. And then the last one you hear is constant, and that's the ones that we've been dealing with before, and you're going to follow this one over here. Okay, so let's look at example 1. What I'm going to do first in this example is I'm going to label everything in here. So let's read it once. It says the rabbit population increased by 34% each year. If the initial population of rabbits was 1,500, what would the population be after 4 years? It says write the equation, then solve. So if I go through here, it says the rabbit population increased. So since it says the word increase, I know it's a growth. And I know I wrote growth here in the example, but in tomorrow's video, I won't be labeling if it's a growth, decay, or constant. You have to know that just by the words. So since it says increase, we know it's a growth. And then this right here, this 34% is our B value. But since our B value has to be a decimal, we have to turn 34% into a decimal. So if we look at the decimal point here and move it 2 to the left, this becomes 0.34. Okay? Then it says if the initial population of rabbits was 1,500. Remember, initial is our A value. What would the population be after 4 years? So this is time, so this is x. This says write the equation. So we have y is equal to a, which is 1,500, parentheses 1 plus, since this is a growth, 0.34 to the power of x. This is our equation part. So this is the equation part. So remember, in an equation, you always have y and you always have x. So we have y and we have x. To solve it, we're going to plug in 4 in for x. So we have y equals 1,500. And I'm going to simplify this here. 1 plus 0.34 is 1.34 to the power of 4. So if I plug this into my calculator, I will get an answer. So let me see if I can do this on my phone. What would be the easiest way for you guys to do it? So you are able to do this on your phone. So if you go to the calculator on your phone, first do this part right here. Let me highlight it. Do this part. Oops. Didn't click on it. Do this part first. It won't let me highlight. Sorry, one moment. Do this part first on your calculator. So do 1.34, and then if you turn your phone to the side, there's a button that says x to the power of y. Click that, and then click 4. Okay, and then that gives us a number. So then this is now y equals 1,500 times 3.22. Then I'm going to multiply that by 1,500. And then I get 4,836. Remember, we are dealing with the rabbit population, so we can't have 0.26904 of a rabbit. So this is what it came out to on the calculator. So since we can't have that amount of a rabbit, we're going to go ahead and round up. So this is approximately 4,837 rabbits. Okay, that's going to be our answer. So remember, it said initially it started with 1,500 rabbits, and then after 4 years, we have 4,837 rabbits. 1,500 is smaller than 4,837. And since it was an increase, that was supposed to happen. Our number was supposed to get bigger. Okay, let's look at example 2, decay. So I'm going to read the problem first. Mr. Clark told his English class that each week students tend to forget 16.7% of the vocabulary words they learned the previous week. If the student learned 30 words, write an exponential equation to describe the number of words forgotten after 5 weeks. So remember, first we're going to go through and label everything. So let's see, Mr. Clark told his English class that each week students tend to forget. Forget means it's a decay. And we're looking for those keywords. 16.7% is our B value, but we have to turn it into a decimal, so it's going to be 0.167. Remember, we move that decimal 2 places to the left. If the student learned 30 words, so this is what they initially know, our A value, write an exponential equation to describe the number of words forgotten after 5 weeks. This is our time, so it's x. Okay, now we can plug everything in. So for our equation, remember we have to have y and x. So I have y is equal to a, which is 30, 1 minus, because it's a decay, 0.167 to the power of x. And then to solve it, we plug in x. So y is equal to 30. Let me simplify this. 1 minus 0.167 is 0.833 to the power of 5. So remember, I do this part first on my calculator on my phone. So 0.833 to the power of 5. So I get y is equal to 30 times 0.401. And then I multiply by 30 times 30. And then I get 12.0322, yada, yada, yada. So I'm going to round that to approximately 13 words. So what this is saying is that if the students learned 30 words, after 5 weeks, they will only remember 13 of them. So they learned 30 words. After 5 weeks, they only remember 13 of them. 13 is smaller than 30, so it decreased, which is a decay, and that's what we were looking for. Okay, let's look at the last example, which is a constant. It says you invest $200 when you turn 18 years old every 4 years. How much money will you, there's a mistake there. How much money, let's erase this one right here. You are told your money will double. How much money would you have when you are 42 years old? So it says you invest $200 when you turn 18 years old. You are told your money will double. How much money would you have when you are 42 years old? Okay, so we're going to go ahead and label everything. So it says you invest 200. So that's what you start off with. So this is your A value. You are told your money will double. Notice that there's not a percent anywhere in this problem. That's how I knew it was a constant. So if you don't see a percent, you have to know it's a constant, and you have to look for the number or the word that tells you what number our constant is. So it says you are told your money will double. Double means 2. So this is your B value. How much money will you have when you are 42 years old? So this is our X value. But what we have to do is we have to take 42 minus 18 to find the total years that you invested. And then that's going to be our X value. So 42 minus 18 is 24. So 24 is equal to our X value. So that means you had your money in the account for 24 years. So then I'm going to do our equation is y equals our A value, which is 200, times our B value, which is 2, to the power of x. Okay? And then I'm going to solve this by plugging in x. So I have y is equal to 200 times 2 to the power of 24. So first I'm going to do 2 to the power of 24. 2 to the power of 24. It's going to be a big number. So this is 200 times 16, 777,216 times 200, which is equal to 3355443,200. Okay, so obviously this problem is made up because it's saying that you will have a bunch of money in your account after 24 years. So if you put $200 in a bank account when you turn 18, by the time you turn 42, you should have $3 billion in that bank account. This is just a make-believe problem. But going off the numbers they gave us, this is correct. Okay, So you learned about growth, decay, and constant.